In this video, I'm going to tell you about the IP service that's provided by the network layer in the 4-layer internet model. In many ways, IP is the most important layer of the internet because whenever we use the internet, we're required to use the IP service to send and receive our packets. Now that I've described the 4 layers of the internet model, we're going to move on and look at the IP layer in more detail. And I'm going to describe this in terms of the IP service model. That is, what service does IP provide to the layers above, and what does it expect from the layers below? So as we know, the network layer is the second one up from the bottom, and if it's sitting below TCP, it's responsible for taking TCP segments, putting them into a datagram, and then sending them through the network. The IP service model is very simple. Here are its main properties shown below. So the first thing is it's a datagram service. The datagram service means that they are individually routed packets using packet switching, and that they go hop by hop through the network. That means each router is going to make its own independent decision, just like a mail sorting office does when it's processing letters. And that's where the name datagram comes from. The next property is that it's unreliable. Unreliable means packets might be dropped. We make no promise that when packets are first delivered, when they are delivered through the network, that they won't be dropped along the way. This was actually kind of a shocking thing to suggest at the time that the internet was created, because up until that time it was assumed that networks would reliably carry data. So this wasn't considered to be the responsibility of the IP network layer. However, it isn't allowed to just willy-nilly just drop anything. It's required to be best effort. What that means is it will only drop them if necessary. It isn't going to arbitrarily drop them on the floor just because life's getting a little bit tricky. It will only do so if it's run out of resources or there's a genuine failure in the network. So for example, if a buffer in a router was to fill up, then the packet will be dropped, and that's considered okay. However, it's not okay for a router just to randomly throw packets away just because it feels like it. Finally, IP is connectionless. What this means is that before communication takes place, there is no per flow state that's established in the network. If we think about how a circuit switch works, in a circuit switch network, it must establish state prior to the communication taking place. In the IP service model, there is no per flow state. It also means that because packets are individually routed, hop by hop, they can potentially take different paths, and it means that packets and therefore the data might become missequenced as it passes through the network. So it may come all as a little bit surprising, and you may be wondering what these internet inventors were thinking of when they created such a simple model in the first place. But it turns out that this is an extremely powerful model and contributes a lot to the success of the internet. So essentially what IP does is it makes a good effort to deliver packets without any guarantees. It makes very little expectation, it has very little expectations of the link layer running below, which could be wired or wireless. And in fact, it makes such a little expectation, or has so few expectations about the link layer, that many people have said that you could run it over almost anything. So for example, there's even a standard, somewhat tongue-in-cheek, telling you how to run IP over a carrier pigeon network. So this simple model of IP made sense because the internet was created to interconnect existing networks. So it was easier to require very little of those that already existed. And it turned out to be a very powerful model, as we all know. Let's take a look at the IP service model in a little bit more detail. First of all, IP has features in it to prevent packets looping forever. We shall see that when we look at the packet format next. It will try and fragment packets if they are too long. Let me explain briefly what this is. Imagine that we have a router connected to another router and a packet is flowing through, let's say over here. Let's say that this link is allowed to carry packets up to 1,000 bytes long, whereas this link is only allowed to carry packets up to 900 bytes long. When the packet finds its way over to here, if it's a 1,000 byte long packet, this router has to decide what it's going to do with it. And so in the IP service model, it breaks it down into 2 packets, One will be 900 bytes long and one would be 100 bytes long. But they both are established to be completely self-contained independent IP packets. This process is called fragmentation. IP uses a checksum in the header to try and reduce the chances of delivering a packet to the wrong destination. It also allows for new versions of IP. Currently we use IP version 4, which has 32-bit addresses, and that's the one that's most commonly used, although IP version 6 is rapidly taking hold to give us more addresses to allow for more people in the world to be connected. And this has 128-bit addresses, which should last us for a very long time. Finally, IP allows for new options to be added to a header for future expansion. Let's take a look at the IP version 4 datagram, and we'll see some of these features showing up. This grayed out area here is the header of the packet, and this portion down here is the data. I'm going to tell you what each of these fields are in a minute. Up in the top left-hand corner is bit 0. This is the first bit that will be sent on the wire by the Ethernet frame that contains it. This is the 32nd bit, bit 31, and so across here is one word of 32 bits wide. So each of the rows here corresponds to a 32-bit word. The first field, the most important field, is the destination IP address. This is the 32-bit address that's going to tell us where the packet goes. Also, the source address is going to tell us where the packet came from. And the protocol ID is going to tell us how we should interpret the data. So it's essentially telling us what is the data inside. So the most common one is that the protocol ID equals TCP, which tells us that the data inside is a TCP segment. The next field is the version. So today this would most commonly be that the version equals 4, and in future it'll be common for this to be 6. The total packet length tells us how long the packet is, right from the beginning all the way through to the end of the data, and this has to be less than 64 kilobytes. The time to live field is what helps prevent packets from looping forever. When the packet is sent into the network, it has a fixed value to start with, and then at each hop along the way, each router is required to decrement this by 1. If it ever reaches 0, then the router is required to drop the packet. What this means is that if a packet was to be stuck in a loop forever, eventually its TTL would be decremented by a router to 0 and the packet would be dropped, therefore preventing the packet from going round forever. This set of fields here are all to do with fragmentation, and we're going to learn about those in a later video. The type of service tells us how the packet is to be processed by a router. Is it to be given preferential service? The header length tells us whether there are any options in the header. So if the header length is the minimum value, it tells us there are no options. And if the header length is larger than that, it tells us that we're going to find some options down here which are for extensions. I'm not going to describe any of those here. Finally, the checksum is calculated over the entire header to try and make sure that if there are bit errors along the way, we'll catch them and prevent or at least minimize the chances that we'll accidentally deliver the packet to the wrong destination. People often refer to an hourglass model of IP. That's because whenever we use the internet, we're required to use IP. It really defines the core of its operation. IP is designed to operate on any type of link layer or physical layer that runs below, like Ethernet, Wi-Fi, DSL, cable TV, etc. And we can run lots of different transport protocols on top, TCP, UDP, and we'll see some others later. And on top of that, we can run many, many applications. But it's the thin waist, the hourglass model of IP that really defines the core operation of the internet, over which everything must run. In summary, we use IP every time we send and receive packets in the internet. It provides a deliberately simple service. This was designed so that it could operate over lots of different types of network, and we could leave the details of reliable in-order delivery to transport layers that run on top. IP provides a simple service of datagrams that are unreliable, they may be dropped, best effort in that we only drop them if we've run out of resources, and connectionless in the sense that there is no per flow state and datagrams may be delivered out of sequence. This is the end of the video on the IP service model.